All right, so now that we have done the expected value of the variable, that's how you calculate it, saw that in the last video, we're going to do the variance and the standard deviation. And if you remember variance and standard deviation from chapter 3 here, where we had John and Robert's parts companies, and just to review that, here's the number of days they took to deliver parts at John's company, here's how many days Robert took to deliver parts. Over 5 days, right, they had a total number of 50, which was the number of days in total that it took them to deliver parts over 5 days, 5 different orders. And then average for each of them is 50 divided by 5, which is 10. That's the average for each of them. And then the median for John, just as a reminder, this is another measure of central tendency. The median is 10. That's the middle data. It's got 8s, 2 8s on one side and 2 12s on the other. The middle value is 10. And over here, I incorrectly did this when I came back and looked at this just before this lecture. And I used to have this as 10. It's actually 5. Because at 5, you have 2 and 3 on one side. You have 10 and 30 on the other. So 5 is the median for this one. So if you caught that, great. And if you didn't, pay attention. Point out when I make a mistake. And all humans make mistakes. And then we have the mode. And this one's bimodal. And so it's the value or the values which occur the most frequently. And this one doesn't have a mode because there's no repeating values. And then we have the range, so the difference between, this is a measure of dispersion or variance. These are down here. And the range is like 12 minus 8. Biggest value minus smallest value gives you a range. And here 30 minus 2 gives us a range of 28. So that starts to give us an indication of variance or dispersion of the data. And then we have the actual variance here. And the variance is going to be how much does each data point vary from the mean. So we have this one, 8 minus 10 gives us negative 2, 12 minus 10 gives us 2. But to calculate the variance, right, because the mean is kind of the middle, the mean is the middle, right? So it's the measure of central tendency of all of those values. When you subtract a value from the mean, you're going to get these values, but when you add them all up, you get 0. So that really doesn't tell us anything. So to create a formula which shows us how much the data varies, it shows us the variance, we're going to square these differences between a data point and the mean. We're going to square them. So negative 2 squared is 4, 2 squared is 4. We're going to add all those up, and then we're going to divide it for a sample by n minus 1, and for a population by n. So 16 divided by n minus 1, 5 minus 1, 16 divided by 4 is going to be 4, which is kind of cool because this really shows us that the variance, how much does a data point vary around the mean. And if the mean is 10, we have a variance here of 4, but that's like at a squared scale because we squared everything from the differences to this, so that when we added them up, they didn't just add up to 0. And so we get the standard deviation by taking the square root of this and bringing this back down to like the value that these values were operating at. So the square root gets rid of the square here. And that really shows us very clearly that how much what's the standard amount that the data deviates around the mean? It's 2. The mean is 10, and the data deviates around the mean 2. We go to either 8 or we go to 12. And so that's variance and standard deviation, straight stone cold statistics. You know, that's variance and standard deviation in a straight stone cold statistics way, like just as a basic fundamental application of mean, variance, and standard deviation. But when we're dealing with probability distribution, discrete probability distribution, and a random variable, we calculate the mean like this, right? Where we already saw that, where we multiply the variable, which could be randomly going to be one of these variables, by the probability of that. And then once we've got all those, we add them up. That's how we get the expected value or the mean of a variable, which can randomly be one of the variables, right? That's possible. And so to get the variance and the standard deviation of that, the variance is going to summarize the variability in the values of a random variable. The variance is going to be the difference between a data point and the mean, square it, multiplied by the probability, add all that up. And here's the notation for the variance. And I have that sheet of notations. Let me just show you that for your edification and repetition and practice. And just as a reminder, let me get it. Hold on. So here it is. So the mean for a sample is represented by x bar or mu for a population. For a sample, little n is the amount in the sample. Big N is the number of elements in a population. Variance is s squared for a sample, or sigma squared for a population. Standard deviation is the square root of the variance, so we just have s or sigma. And so those are the little notations there. So here you can see it's sigma squared. So sigma squared is showing us that this is the variance for a population in this formula. But if we were doing variance for a sample, it'd be s squared, and maybe the formula would be slightly different. And then we have standard deviation. Sigma is for a population. That's just going to be the square root of the variance. And the variance is the weighted average of the deviations. So the deviation of this point minus the mean squared of a random variable from its mean. The weights are the probabilities. So this is how you calculate it. This is what we were looking at before, right? Here's how we calculated the mean right here. There's the mean right there. And then over here, we get the difference between a data point, the random variable, and the mean. So 0 minus 1.5. 0 is right here. 0 is right here. 1 minus 1.5. 2 minus 3 minus 4. 5 minus 1.5. And we get those values. And then we're going to square negative 1.5 squared. We can come over here. Actually, we'll do it this way. This is a little bit more visually cool. This is a little bit more visually cool, man. We're going to go to calculator. And we'll do negative 1.5 times. Did that just multiply it? Negative 1.5. I don't know if that did it. All right, negative 1.5. I got to restart this all. Let me make this big and see if I make it big, if it makes everything big. That's kind of cool. So I'm going to hit clear. I don't know what the difference between C and CE is. We're going to figure that out here. All my life I haven't known that. So negative 1.5. And it didn't do negative for me. I'm just going to do 1.5 times 1.5 because I know, oh, now it did it. And then I'm going to do a negative 1.5. And I'm going to do an equals. And 1.5 times 1.5, it's giving me 3. Not liking that. Not liking it. Because 1.5 times 1.5 over here is giving me 2.25. So when you square negative 1.5, so let's try this again. So let's try it up here. Let's see if we get the same thing. And we'll just do 1.5 times 1.5, and we'll see what that gives us. That gave us 2.25 here. I don't know what's going on with that calculator, why it didn't work. Let's try 1.5 times 1.5. Maybe I was thinking because I was doing the negative sign, it was throwing it off. I don't know how to make it negative here. So maybe it's this one here, m negative, right there. And now I'm going to do that, and now we got 2.25. That's what I'm looking for. All right, so 1.15 squared. 1.15 squared right here is 2.25. And then here's the probabilities, 0.8. So take that 2.25, multiply it by 0.8. 0.5 squared is 0.25, negative 0.5 squared is 0.25. Multiply it by the probability, you get this. So here's where you get all those. And then the formula for variance is that we sigma those. We add them up. Interestingly, this is sigma, this is sigma. I'm going to ask ChatGPT that because that just came up as is that right? I'm going to go to my snipping tool, and I'm going to hit new, and I'm going to grab that. Boop, boop, boop. And then I'm going to save it, and I'm going to save it as temp. Come on, baby. And so now it's temp, and I'm going to go back over to ChatGPT, and I need to be in our module 5, statistics, and it's going to take a moment to load in. Come on, load in. Let me refresh you. Oh, there it was. There it's loading in. And now I'm going to hit this and upload from my computer, and that probably went into downloads, and there's temp. And it is are both of those Greek symbols called sigma? The one that represents add it all up, and also the one that represents variance. Let's find out. So I'm thinking, is this one here that represents add it all up? This one represents variance. The two Greek symbols in the image are not the same, and they represent different things. Summation notation, the large uppercase Greek letter sigma, represents the summation operator, And the lowercase Greek letter sigma, so this is lowercase sigma, this is uppercase sigma. I never knew that. We're all always on a learning curve. And did I tell you about dark matter? 95% of the mass and energy in the universe is dark matter. And they call it dark matter because they know it's there, right? They mathematically calculate that that mass and energy has to exist in the universe, but they don't know, they've never seen it. They don't know. They don't know anything about it. So 95% of the mass and energy in the universe is dark matter and dark energy, and we know nothing about it. So it's all right to not know stuff. Like, what's the difference between this and that? They're both sigma. One's lowercase, one's uppercase. Lowercase, uppercase. So that's good. Just learn something. I like it. And the more you do something, the better you get at it. And this is the way you get better at it, is by saying, that's something I don't know. That's something I don't know how to do. That's something I don't know intellectually. And then you practice it, you get it, and then you know it. And then people are like, how do you know so much? Well, I'm really step into not knowing, and that allows me to know. It's kind of a cool paradox. So here we get the variance is 1.25 once we do all that calculation. And then the standard deviation is just going to be the square root of that variance. So how much do things deviate on a standard daily basis? Deviates 1.18 cars. So our mean is 1.5, and we could deviate 1.18 every day on how many we sell. So we might have, like, that's one standard deviation. We might have, like, 2.618 cars sold on one day as our standard deviation over time. And, so that gives you an idea. And then what we're going to see is that the number of standard deviations away from the mean, we could start to say, like, this is going to happen 98% of the time, that, we'll have things within 3 standard deviations, and then 2 standard deviations will happen a certain percentage of time. And then, like, 1 standard deviation will happen a certain percentage of the time. And that's like, what is Chebyshev's theorem? We already looked at this too, is Chebyshev's theorem. And also that 97, 95, 80, 87, or whatever it is, is rule. I'm getting those numbers wrong. What are they? Getting those numbers wrong. What are they? Thank you for helping me learn this stuff. About statistics. I kind of think the way you treat machines is the way they're going to treat us. So that's like literally, like if we treat it like crap and we're just like, tell me, do this. Eventually, that's how the machine will be trained upon all of our stuff, and they'll be treating us like that. And then obviously, if they become robotics, we don't want them to be like that, right? So it'll respond to us. Like, if we're friendly, it responds friendly. That's my theory. You're welcome. I'm glad I can help you. Let's go over Chebyshev's theorem and the rule you're referring to, which is commonly known as the empirical rule, sometimes called 68, 95, 99.7 rule. And so both of these things say that a certain amount of data is going to be within a certain number of standard deviations of the mean. And so for like this rule here, the 68, 95, 99.7, like 99.7% of our data will be 1 standard deviation. So our car sales will be within 1 standard deviation of the mean, which is 1.5, 99 point whatever 7% of the time. And then 2 standard deviations, it'll be 95% of the time. And I'm just thinking if I'm saying this right. We'll read through this and see what they say. And then 3 standard deviations. I kind of think this should be 3 standard. Like that's all of it. Let's read it. The empirical rule applies to normal distributions, bell-shaped symmetric distribution. Tells us how data is distributed in the normal distribution. 68% of the data, that's right. 1 standard deviation. So the more standard deviations, it captures more data. So 95% of the data, 2, and 99.7 is 3 standard deviations. So 99.7% of our days, we're going to sell between -3 times this and +3 times this around the mean. And that will be 99.7% of our business. So from 0 cars all the way up to like 5 cars, which is what we have listed there. And that'll be 99.7% of the time. But if we narrow that down, 95% of the time will be within 2 standard deviations. And so that will be like 2 times this will be like about 2 plus 1.5. That will take us to like 4. So 95% of the time we're going to sell between 0 and 4 cars if this is a normal distribution. And then 68% of the time we're going to be within 1 standard deviation. So from like 0 to 2.5 or 3. From 0 to 3 is going to be 68% of the time. And so that's like where knowing the standard deviations can start to tell us, it gave us more insight about our data with the empirical rule, and then also Chebyshev's theorem, which also is a measure of like, you know, how much data is within how many standard deviations. And it looks like ChatGPT kind of didn't get that right here. It's trying to create a formula, but it didn't work. And so here, statistical rule that applies to any distribution, regardless of its shape, whether it's normal, skewed, bell-shaped, right? It provides a way to estimate the minimum proportion of data points that lie within a certain number of standard deviations from the mean. The theorem states that for any data set or probability distribution, at least 1 minus 1 over k squared of the data falls will fall within k standard deviations of the mean, where k is greater than 1. In other words, it tells us that no matter what the distribution looks like, a certain minimum percentage of data must lie within a given number of standard deviations from the mean. And so key differences applies to all distributions, Chebyshev's, regardless of shape, but gives a minimum percentage of data within a certain range. And empirical rule applies to normal distributions. It gives a more precise percentage of data within 1, 2, and 3 standard deviations of the mean. So Chebyshev's theorem and the empirical rule. And then I want this to regenerate. I don't know, read aloud. I'm going to hit bad response, I guess. And shouldn't have used memory. Don't like the style. Not factually correct. Didn't follow instructions. Refused when it shouldn't have more. I'm going to say optional here. Unsafe or problematic. Being lazy. Maybe being lazy. I'm going to click other. And I'm going to say it didn't calculate the formula for Chebyshev's theorem in its entirety. Being lazy. I don't know. Being lazy. That's interesting. Can you please regenerate that response and fully calculate all of this stuff? So it displays correctly. So I'm going to just copy this stuff here because that's wackiness. And I'm going to put that in here. And ba-boom. Bada bing, bada boom. I don't know what that means. All right. Whatever. What's it called? Sopranos, right? Examples of Chebyshev's theorem, at least 1 over k squared. 1 minus 1 over k squared is equals 1 minus 1 over 2 squared. 1 minus 1 over 4. 1 minus 0.25, 0.75. 2 standard deviations of the mean, right? At least 75% of data values fall within 2 standard deviations of the mean. 88% of the data, 88.89% of the data fall within 3 standard deviations of the mean. Perfect, thank you. I don't know what this little thing is. Change model? No, I want that. Perfect. Thank you, you're amazing. Thank you, you're amazing. Let's see what it says to that. It's not saying anything. It must be like totally overworked. Thank you so much. I'm really glad I could help. If you ever have more questions or need assistance with anything else, don't hesitate to reach out. You're doing great. Keep up the awesome work with your studies. That's so fun. I love it. All right, that's what I think we did. Standard deviation. We did variance and standard deviation in this one. And yeah, that's what we did. And so in the next one, we're going to look at bivariate distributions. And if we come back here, I'm just looking to see if bivariate is here, but we have discrete uniform probability distribution. We did that one. So I'm just going to copy my little guy here and put that there. We did that one. We did binomial probability distribution. There's Poisson, which sounds kind of cool because it's French, and hypergeometric, which sounds like, I don't know. But bivariate, where does bivariate come in? Like right at the very beginning, we have bivariate here. And so we'll take a look. You know, it's like what they're listing here, it doesn't even jibe through what is presented logically through the presentation. Whatever, we're going to do bivariate distribution next. We've done that one, and we've done this one, and we've done this one, and binomial probability distribution, we did that one. And so now we've got these other ones to do. So we're going to do bivariate distributions and covariance. That's coming next. So where are we? Bivariate distribution number 4. See you in the next video. We're going to do that.